hydrogen is coming out. It's not coming out as hydrogen gas, it's not bubbling out of there. I've written 2H, and that 2H is stuck to another molecule called NAD, NADH, nicotinamide adenine dinucleotide. This is another problem with biochemistry. There are all these difficult names, but actually all it's doing is passing on 2 hydrogen atoms. Where's it passing them to? It's passing them into the membrane surrounding that. You can think of this as a mitochondrion or as a bacterial cell or as not one of your cells because the mitochondria are inside your cells. But that 2H are being split up. I'll show you what happens in a moment. But they're eventually reacting with oxygen. And that's what's generating all our energy in the form of ATP. So that energy, this reaction between hydrogen and oxygen, you can think of it as rocket fuel, really. This is what's powering us. This is what's making us alive. In this slide is what makes us different to a corpse. There's no difference in information between a living person or someone who died a moment ago. The information content is exactly the same. The difference is the flow of energy and the flow of matter continuously going through. And this is the core of all of that. The Krebs cycle is spinning continuously in all our cells. Notice there's a kind of a purple thing around that, around the membrane itself. And I've got lots of little H+ signs there. These are the protons. These are the charged nucleus of hydrogen atoms. And what's happening, the energy released from this reaction between hydrogen and oxygen is used to pump protons across a membrane. So don't worry if you're a little bit scared of terms like protons, but basically you've got a charge now on that membrane. I noticed there was an email sent around by the RI yesterday, and it started out about Frankenstein and said, we all think life is about electricity, and actually, no, it's not. Nick Lane's going to come and tell you it's all about chemistry. Well, no, I'm not. It is about electricity. Not quite like Frankenstein, but this cycle, the Krebs cycle, is linked to powering up a membrane, so you have an electrical charge on the membrane. And that electrical charge on the membrane, it's tiny, it's 150 millivolts across the membrane, so it's not very much. But if you were to shrink yourself down to the size of a molecule, so that you were the size of, let's say, a carbon dioxide molecule or something, the electrical force that you would feel there is about 30 million volts per meter. That's the field strength. So that's equivalent to a bolt of lightning, funnily enough, which is what brought Frankenstein to life. So we have this, from Frankenstein's monster, we have this going on in all our mitochondria, in all our cells, all the time. Now, I've just drawn this circle to keep things simple. This is what mitochondria actually look like. And you can see they've got these very thin membranes. These are called the Christie membranes, and this is where all this proton pumping is going on. So if you were to iron out all of these membranes from your own body, it would be about 4 football pitches worth of membrane, which is charged like a bolt of lightning. That's what makes us alive. And that charge will flicker and die if we're not keeping on turning the Krebs cycle. So that's why the Krebs cycle is so central to what's going on with life. Now, what I'm just showing down at the bottom there is a kind of cartoon of this process. So the 2H, the 2 hydrogen atoms, are split into the component parts, into electrons and protons. The electrons are passed in a kind of a wire inside the membrane, so we have a current of electricity inside the membrane flowing to oxygen. That current of electricity powers the extrusion of protons across the membrane, so we have this electrical charge on the membrane. And then they flow back through a turbine, in effect, the ATP synthase, which is at the right-hand side. So it's basically like a hydroelectric dam, where the membrane is equivalent to the dam, the proton reservoir, if you like, is equivalent to the reservoir, and the ATP synthase, well, it's a rotating motor. It's an extraordinary protein. This is another reason why biochemists don't like to ask why. How on earth does something with that majesty evolve? It's plainly a product of genes and natural selection and so on, but when I think about these questions, I'm wondering about how did it arise in the first place. It's a strange fact, but basically all life on Earth works this way. This way of generating electricity is as universally conserved as the genetic code itself. This is how cells work. Bacteria work this way, archaea work this way, plants, animals, everything works this way. So there's something profoundly important about how it works, and yet it's very difficult to wrestle with in terms of how does it happen. These are two of the most important discoveries, in my opinion, in the 20th century of science. One of them, that the mitochondria themselves and the bacteria work in the same way, are basically electrical fuel cells, was discovered by Peter Mitchell. And I want to say, and Jennifer Moyle, because Jennifer Moyle did all the experiments. Mitchell was a genius who thought things that nobody else had really ever thought before. But a lot of people thought he was a madman, insane, and really would practically leave the room if he came in. He really infuriated people. It was Jennifer Moyle's experiments that made other people take Mitchell seriously. And it's a sorry state of the world that Mitchell himself got the Nobel Prize in 1978, but Jennifer Moyle was overlooked, which I think would not happen today, let's put it that way. The other person on there is Lynn Margulis. She really nailed the idea that mitochondria were once bacteria. So mitochondria, the power packs in our own cells, once were free-living bacteria and were acquired 2 billion years ago, probably, in the course of the evolution of complex cells. And so these power packs that we have were once free-living bacteria. These are two of the most important discoveries that, again, I think everybody should know.